Welcome to the final lecture of the Haskell course. We already covered everything you needed to know to start working with Haskell in previous lectures. So this one is going to be different. We're going to build a non-trivial project, we're going to go fast, and I'm going to assume that you already know the basics of the Haskell programming language. We're going to build a CLI that transforms Markdown files into HTML files. Let's see how it works. If we open the terminal and we type md2html-help, we'll see a helpful description of what the tool does. It contains a short header, how to use it, a longer description if needed, and all the available options. And as we can see in the available options, all we have to do is provide the path to the Markdown file with the -i option and provide the path where we want the HTML file to be with the -o option. So let's try it out. As you can see, I have a single file in this directory. And if we open it with NeoVim, we'll see that the input.md file contains one level 1 title, one paragraph, a level 2 title, another paragraph that contains both bold letters and italics, then an order list with the second item containing bold text, another paragraph, an unordered list, and the final paragraph. Now, let's close this and run the CLI. So we have to run markdown to HTML, -i, and the name of the input file, -o, and the name of the output file. And if we run this, we won't see anything because we didn't use the verbose flag, but if we list the contents of the directory, we'll see that we have the output.html file. And of course, we can open the output.html file to see that it was indeed correctly transformed. Okay, now that we know what we are building, let's get started. We're going to split the development of the CLI in 3 different stages. First, we're going to develop the CLI itself, meaning the way we interact with this tool. Then we're going to build the parser that is going to interpret the contents of the Markdown file. And finally, we're going to build the HTML generator that is going to generate the new contents of the file. Let's start by creating a new empty directory and running cabal init with an executable. Once the project is ready to go, let's open it and go straight to the cabal file. And then let's go add the source folder. Now that we are here, let's take the opportunity to add the CLI module that we are going to create later, the overloaded strings extension, so we don't have to activate it every time, and finally the opt-parse applicative and text libraries. Since we are going to read and write text files, the standard library string type, which is just a linked list of characters, may be too inefficient. That's why we're going to use text. Text is a library that provides an efficient Unicode text type and a bunch of functions and utilities that make it easy to work with. Every time you're working with non-trivial amounts of text, you most likely want to use this library. The other dependency that we added is opt-parse applicative. It provides utilities and combinators for parsing command line arguments. It takes care of reading and validating the arguments, handling errors, provide help screens, and many other things. On top of that, it's really easy to use and it has great documentation. So this one is going to be your go-to library to write CLI applications. If you scroll a little bit, you will find a great introduction. However, I'm going to skip this and go straight to the module. The options.applicative is the main module of the library. And as you can see, it's also thoroughly documented. If we go to the running parser section, we see that we have the exec parser function that takes a parser info A and returns an IO A. In this case, A is the type of the value that we want to get back from the parser. So if we only need to parse a string, A will be a string. If we need to parse a boolean, A will be a boolean. And if we need something more complex, we can create a custom data type. Okay, we have something already. Let's start coding. Let's go back to our project and create the source directory with a cli.hs file. Inside the file, we initialize the module, import options.applicative, and create the CLI Parser function. We know we want to execute the parser, so we start with the exec parser function. exec parser needs to be applied to a value of type parser info a. And if we look at the documentation, we'll see that this type contains all the information about our program, its description, header, footer, etc. This is used to generate our CLI help screen. If we scroll a little bit to the top, we'll see that a parser info should be created with the info function applied to a parser and a set of info mod modifiers. So let's split our problem and create the options and info modifiers functions. Let's start by implementing the info modifiers. If we go to the documentation, we'll see that info mod doesn't provide its constructors. However, we have a bunch of helper functions, and we can see that info mod is an instance of monoid, so we can pick and choose the ones we want and combine them with the semigroup operator. We have many options. In this case, we are going to pick full desk to show a full description in the help text, header that takes a string and specifies a header for the parser, and proc desk, which takes a string and specifies a short program description. So let's go back to our info modifiers function and add full desk, combine with proc desk and an appropriate description, combined with the header with a short header description. And that's it. We are done with info modifiers. Now let's go back and see how we can implement the parser. The parser's data type constructors are also hidden. However, we get a bunch of parse builders that we can use. Notice as well that parser is an instance of alternative and applicative. In our case, applicative's behaviors are going to come in handy. If we scroll down a little bit, we're going to find the string option builder. It takes a mod option fields s, where s is a type that is an instance of isString, and returns a parser of type s. Since this is a builder for an option that takes a string argument, we can use it for both the input file and the output file paths. Let's see what this mod type means. Okay, so mod is an option modifier. Option modifiers are values that represent a modification of the properties of an option. We can also see that mod has an instance for the monoid and semigroup type classes. If we scroll down a little bit, we'll see that we have many functions that return an option modifier. For example, short takes a character, returns an option modifier, and specifies a short name for an option. We also have long, which takes a string and returns a modifier that specifies a long name for an option. We also have help, which takes a string and returns a modifier that specifies the help text for an option. And we can keep going and going. However, we're just going to use these three and metavar. Metavar takes a string and returns an options modifier that adds a symbolic name for an argument to be displayed in the help text. This is going to make our help text a little bit nicer. Okay, so let's go back to our editor and write our first parser. We're going to start with the path to the input file. So we'll use string option, and for modifiers, we're going to provide a short name of I, a long name of input, a help description that this corresponds to the input file they want to process, and a meta variable of input underscore file. And this is actually good enough to start testing it. So let's go to our main file, import CLI Parser from the CLI module, run our CLI Parser to see what we get, and print the result. And now to test it out, we can open a terminal, run cabal build, clear the terminal, and cabal run. And it worked. Since we didn't provide the input file, it just showed the help text, which is what we wanted. Now let's test what happens if we actually provide the input file. To provide arguments to our CLI, we can use the double dash syntax. So now we're going to execute cabal run, double dash, markdown to HTML, -i, and the path to the file. And as you can see, it correctly parses the contents of the argument. However, we also wanted to provide the output path and the verbose flag. So let's go back to our CLI module and create a structure that contains all the information that we want to get from the CLI parser. We'll create the options data type that contains the input file of type string, the output file of type string, and the verbose type of type boolean. Now we need to figure out a way to somehow construct a parser that returns an options type. Well, let's do it step by step. We already have the options constructor that is going to return an options type. We just need to apply it to all three values. Luckily, we already have the first value figured out. The string option that we previously defined returns the input file of type string. And since parser has an instance of functor, we can just fmap the options constructor. Let's change the resulting type everywhere. And now we have a parser for a partially applied function. For this to be valid, options needs to be applied to the other two fields. Luckily again, since parser is an instance of applicative, we can just keep applying the function at the parser level. The next field is the output file. So we can apply our constructor to another string option that has a short name of O, a long name of output, some help text, and a meta variable of output file. Finally, since the verbose flag is a boolean, we can find in the documentation that we can use the switch parser, which takes the options modifiers and returns a parser bool. So, to get the final field, we apply the constructor to a switch parser that has a short name of v, a long name of verbose, and some help text. In this case, the meta variable is not necessary. Before moving on, let's go back to our terminal and test our implementation. Let's build and clear to have a blank slate. And if we run the same command as before, we'll see that we get an error because the output file path is missing. We don't get an error about verbose because the switch flag defaults to false if it's not present. Let's run it again, but now specifying the output with the long name. Perfect, the parser worked as expected. One thing missing though is the help argument. If we run markdown to HTML --help, we'll see that it's an invalid option. This is such a common usage though that opparse applicative provides a helper function that we can apply directly to our parser. So let's go back to our CLI parser and apply helper to our parser to get our final expression. And if we check now, we'll see that we can now use the help command and we get a much nicer help text. And that's it for the CLI. Now let's move into the Markdown parser. We'll start by adding the megaparsec library. Megaparsec is a feature-rich parser combinators library. It's very powerful and is widely used in the industry. In contrast with optparse applicative library, which was made specifically to deal with CLI inputs, megaparsec can be used for any general parsing purpose, like parsing your own custom-built language, parsing configuration files, or what we're going to do today, parsing Markdown to then transform it into HTML. We'll go to text.megaparsec, the library's main module, and there we can find everything we need, including a very well-written tutorial that will get you up to speed if it's the first time you use it. Since we are going to create a very simple parser, I will skip most of it. However, I would recommend going through the tutorial before trying to implement this by yourself, so you can understand the underlying decisions and trade-offs of the system. Okay, let's start implementing. Let's go back to our editor, add the mdparser module to our cabal file, and create the actual module. We'll start by creating a type alias for our Markdown parser. It's going to be called mdparser, and it's going to be the same as the parsec type constructor applied to void and text. We import text from the data.text module, void from the data.void module, and of course, parsec from the text.megaparsec module. Now, parsec is a type synonym for the parsec t type applied to the identity type. Parsec t is the central data type of the megaparsec library, and it's actually a monad transformer. We didn't cover those in this course. However, we don't need to, because when we apply a monad transformer to the identity type, we get a non-transformer variant. And we do know how to use those. But what about the E and S type parameters that we apply to void and text? E is the type of custom component of error messages. Since we don't want anything custom, we're going to use void. And S is the type of the input stream. Megaparsec works out of the box with string, strict and lazy text, and strict and lazy byte strings. In our case, we are going to use strict text from the text library. That means our parser will be able to consume the characters of our Markdown file as a stream of text. And if there's an error consuming those characters, we'll get the default error mechanism that comes with Megaparsec. Now, the whole point of parsing this stream of text is to provide structure to our information that then we can use to generate HTML. This structure is going to be an abstract syntax tree that is going to hold just the right amount of information. Let's slowly build up our program by each time creating the node of the syntax tree that represents the type of text and the function that parses the stream of text to that node. Once we have several individual parsers, we can start combining them. The first one is going to be plain text. Imagine we have a Markdown file with only plain text. How could we parse it? Let's start by defining the structure of our syntax tree with the data Markdown element type, which for now, since we only have plain text, is going to have a single constructor called plain text that is going to contain the text type from the text library. And now let's define the parse text function that is going to be a Markdown parser that returns a Markdown element. If we sort through all the available combinators in the library, we'll find an interesting one, the take while 1p combinator. It takes the name of the token that we want to parse and a predicate that we're going to use to test each token of the string. Take while 1p is going to keep parsing tokens until one doesn't satisfy the predicate. And if it can't parse at least one token, it fails. So we will use take while 1p and apply it to just an explanation of what we are expecting, which is plain text, and the predicate, which in this case is checking that the text doesn't contain a star or an underscore, which will mean it has bold or italics, nor the new line character, to avoid merging multiple paragraphs in a single blob of text. And this should work. However, as we can see in the diagnostics, take while 1p returns a parser of text, and we need a parser of md_elem. So we have to fmap plain text to get our final expression. Let's try it out by opening a terminal and running cabal REPL. To set up our playground, let's set the overloaded string extension and import text.megaparsec and md_parser. And now we can use the parse test helper function to check if our parsers behave as expected. It takes a parser as the first argument and the input to parse as the second argument. So we can write parse test and apply it to our newly created parser and whatever text we want. For example, if we parse first try, we'll see that the result is a plain text containing the first try text. But if we put try on italics, we'll see that the parser stops right before the first star character. This is exactly what we need to make sure we don't bother the parser that comes next, which in this case is italics. So let's create it. We'll start by defining the parse italic function that, of course, is an md parser that returns our Markdown element, and we'll start the definition the same way we're going to do most of our parser definitions, by defining a label. The parser label doesn't change the behavior of the original parser, but whenever the parser fails without consuming any input, it improves the error explanation by replacing the names of expected tokens with the name that we are providing. In this case, instead of saying expecting underscore or expecting star, it says expecting italic text. Now we have to define the actual parser. In Markdown, we indicate when something is in italics by putting the part in italics between stars or between underscores. Luckily, Megaparsec re-exports the between combinator from the parser combinators library. Between takes three applicatives, the open, close, and contents applicative, and it returns the value of the contents applicative if both the open and close succeed. Now, for the open and close parsers, we have a few options. but we're going to go with the chunk combinator. For the chunk combinator, the only thing we have to provide are the tokens that we want to match for. So we're going to parse between a chunk that starts with a star and another chunk that ends with a star. And now we have to choose the parser for whatever is between the stars. For now, we are going to assume that that can only be plain text. This might look okay. However, if we only do this, we lose the information that those contents that we are parsing with the plain text parser were between stars. So we are going to create a new node and store the contents within that node. We're going to call the node italic, and it's going to store a Markdown element, and we're going to fmap it to the results of our parser. And that's it. That should work for this case. However, remember that we can also indicate italics using underscores in the same fashion as using the stars. So we can replicate the same logic, but replacing the stars with underscores, and use the alternative binary operator to provide it as an alternative. Now, if the star variation fails, we're going to try the underscore variation before giving up. And that's it, we're done parsing italics. Let's quickly go to our playground, refresh, and try parsing a correct sequence. As you can see, if we parse star something star, we get an italic node that contains a plain text that contains the something keyword. Exactly what we wanted. However, if we remove the final star, we'll see that we get an unexpected end of input and that the parser was expecting either the star to finish italics or the plain text to keep going. And if we do it the other way around, we have underscore at the end, but we don't at the beginning, we'll see that our parser is expecting italic text. If we keep going, implementing the parser for bold is pretty much the same thing. So we can add our bold node to our syntax tree, duplicate the parse italic function, rename it, change the label, constructor, and the open and closing parsers, and we're done. We can go back to the playground, reload, and do the same 3 tests again. If everything is okay, we return a bold containing a plain text that contains the actual contents, else we get the respective error. Okay, so we have 3 independent parsers, but in reality, a line of text could contain any of them. So we need a way to say, okay, here's a line, choose the right parser for it. And that's exactly what the choice combinator does. Choice takes a foldable of parsers, for example, a list of parsers, and applies the parsers in order until one of them succeeds. So we can create a parse line parser, which makes a choice between parse bold, parse italic, and parse text. It's important to choose the right order to avoid unexpected results. For example, if we put parse italic before parse bold, parse line will never be able to parse bold because it will always pick up the first star or the first underscore and interpret it as italic and then fail. And with this, we are ready to do some refactoring. Our initial implementation of parse italic and parse bold assumed that inside there could only be plain text. However, in the real world, we could have bold inside italics and vice versa. So we should change the parse text in their definitions into parse line. That way, we'll keep parsing recursively until it's done. We can showcase this by going back to our terminal, refreshing, and trying parse line with triple underscore. And now that we have a good foundation to build upon, let's create the parser for the headings. In this case, having a constructor with the contents is not enough, because we don't only need to know if it's a heading, but also which level. That way, we can transform a level 1 to an H1, a level 2 to an H2, etc., etc. So we'll add a new heading constructor that contains the level as an int and its element as a Markdown element. Then we create the parse heading parser with the heading label. We know that headings always start with the hash character, and megaparsec conveniently provides the char parser, but the char parser only works for a single character, and chunk parser works for a specific string, but the headings can have a variable amount of hashes. So what do? Well, we can use the sum combinator that applies the parser one or more times and returns a list of values returned by the parser. Notice that sum will fail if there's not at least one hash. This is perfect since we don't want to parse anything other than headings. So we can import text.megaparsec.char, parse the hash character, and apply the sum combinator to make sure we can handle a variable amount of hashes. And since at this point we have a list of hashes, we can fmap the length function to get a parser that returns the int representing the level of the heading. But wait a minute, both Markdown and HTML can have at most 6 levels. So we have to somehow check that the level is never bigger than 6. No problem. Since we are inside a monad, we can import the control.monad module and use the whenHelper function to decide what to do in the case that the length is bigger than 6. In this case, since Parsec implements the monad fail tab class, we have available the fail behavior that we can use to fail with a helpful message. Okay, so what comes next? Well, after the hashes, there's always a single space and then the contents of the heading. We don't care about that space, so we can use the space one parser to skip one or more whitespace characters, and then the parseLine parser to parse the rest of the line. With that, we have the whole thing parsed, but we have to return a heading constructor with the level as the first parameter and the result of the parse line as the second parameter. So we can fmap the heading constructor applied to the level over the parse line to get the final result. If we go to a playground, refresh, and run parse test, parse heading, and we try to parse 3 hashes, space, and let's say the text third level, we'll get a heading of level 3 containing a plain text of third level, exactly what we needed. Parsing a paragraph is even simpler. Since a paragraph can contain multiple different Markdown elements, we can create a paragraph constructor that holds a list of Markdown elements. And now we can create the parse paragraph function with the paragraph label. A paragraph is just space followed by some lines and then more space. So we just have to replicate that in our code. We don't particularly care about the space before and after the paragraph. We just know that it's there. So we can use the skip many combinator that applies the parser 0 or more times, but skipping the result, and apply it to space 1. That way we can skip the entirety of the whitespace. From here we can assume that we are starting a new line. So we could use our parseLine parser. But we already said before that a paragraph could contain multiple Markdown elements. That means that we should run the parseLine parser as many times as possible. So we're going to use the sum combinator to get a list of all the Markdown elements in the paragraph. After this, we should be right at the end of the paragraph. So we can do the same as before and skip all the white space until the next element before finishing. At the end, we have to return all the elements of the paragraph. So we should run the parser to get them and then wrap them in the paragraph constructor lifted to the parser level. And that's it. We can go to the playground and do a quick test to see that it works as expected. Okay, we could keep going and extending our implementation with more and more features, but let's just do one more and then create the main parser that combines all of them. The last one that we're going to build is the parser for an ordered list. We'll start by creating the new type list item that holds a list of Markdown elements. Then we'll create the order list constructor that will hold a list of list items. And now we can start with the actual parser. Same as before, we're going to create the parse order list with an appropriate label. In this case, we're going to call it order list. And since an order list could potentially have multiple list items, we could take a page of the book of the heading or the paragraph implementation and use sum to apply a parser as many times as needed. So we're going to fmap the order list constructor to whatever the result is from the sum parse list item parser. That reduces our work to figure out how to parse a specific list item. So let's create a where clause where we're going to define our parse list item function. Each line in a numbered list starts with a number, a dot, some space, and then the contents of the line. We can use the char parser for the dot and the space1 parser for the space. But what about the number? You guessed it, megaparsec provides the digit char parser that parses any digit base 10. So we can check that the line starts with the correct format by running digit char and then the character dot and then space. And since we don't need the information, we use void to throw the result away. Remember that HTML list tags don't have numbers. The numbers are calculated automatically when rendered by the browser. So we don't need to hold to this information, we just need to know that it's there. The information that we do need to hold are the contents of the list item. So we can do the same as with paragraphs and parse the line, saving all the elements that it contains, skipping the rest of the space, and returning the list item constructor wrapping these elements. And that's it. Let's go to the playground, refresh, and showcase that our ordered list parser works as expected. In the preview, I showcased a Markdown file that also had unordered lists. If you want that to work, you'll have to implement it yourself as homework. It's pretty much the same thing as order list, so it will take you just a couple of minutes. Now let's start combining parsers. Same as we did with parseLine, we need a parser that can choose which parser to use. We're going to call it parse group, and it's going to choose between the parse heading, parse order list, and parse paragraph parsers. Remember that the order matters. And with this, we are now ready to write the final and main parser. The main parser is going to parse the complete file. And once it's done, it's going to return a list of Markdown elements. Since we don't know how much space is present between the start of the file and the first Markdown element, we are going to skip many spaces before we start parsing. Same as we did with other group parsers, we use the sum combinator to apply the parse group parser as many times as needed until there's no Markdown element to parse. If there's no Markdown element left, that means that we should be at the end of the file. So we should be able to run the end of file parser that only succeeds at the end of the input. Once the end of file parser succeeds, we know that we successfully parsed the whole file, so we can return the elements. And that's it, we finished our parser. Now let's integrate it with our CLI and try it out. Let's go back to our main module, and since we now need the information from the CLI parser, we will use the record wildcard extension to easily extract all the fields from the options type. Then we can remove the print statement, import data.text.io from the text library, and use it to read the contents of the input file. At this point, we could optionally provide some information to the user. So we're going to import when from control.monad, and when verbose is provided, we're going to print some information: the path to the input file, the path to the output file, and the contents of the input file. Okay, we have everything ready to run our parser. If we go to the running parser section of the documentation, we'll find the run parser function. It takes the parser to run, the name of the source file, and the actual input for the parser, and it returns either an error or the result. So we import main parser from our md parser module and run parser from the text.megaparsec module. Then we create a case expression where we apply the run parser function to main parser, the input file, and the file contents. In the case that we get an error, we just print the error, and in the case that we correctly parse the elements, for now we will check if the verbose flag is active, and if it is, print the elements. To verify that everything is working correctly, we can create the input.md file and populate it with a bunch of Markdown elements. Then we can run our CLI using the verbose flag and indicating the input and output files, and check the result in the console. Now that we have our Markdown in a format that our program can understand, let's use it to generate the HTML. Let's go to our Cabal file, add the toHTML module, and then create it. we want to convert everything to text because eventually we're going to write it to a file. So let's import the text library and activate the overloaded string extension. And we want to convert them from our abstract syntax tree. So let's import our types from the MD parser module. Our parser returns a list of Markdown elements. So let's create the function toHTML that takes a list of Markdown elements and produces text. We're going to fold the list where in each step we're going to take the element and the accumulator, transform the element to HTML, and concatenate it with the accumulator. And of course, we're going to start with an empty text. Now, in a where clause, we're going to define the lm2html function that takes a Markdown element and returns text. In the case of plain text, we can just return the text. It's going to be valid HTML because plain text will always be inside another elements tag. This is going to be our base case. In the case of italics, inside we have another Markdown element. So we can open the emphasis tag, concatenate it with the result of recursively applying the lm2html function to the element, and then concatenating it with the closing emphasis tag. In the case of bold, it's the same thing but using the strong tag. For paragraphs, it's similar. We surround the elements in p tags. However, because it's a list of elements, instead of using the lm2html function, we can use the toHTML function. The case for heading, it's a little bit more interesting. We have the level of type int and the contents. And since we have different h tags for different levels, we have to dynamically generate the tag. We can do this with the show function from the text library. So we can take the open bracket h, concatenate it with the text representation of level, then with the closing bracket, and we have our opening tag. For the contents, we just have to convert the element to HTML and then do the same as before to generate the closing tag. Finally, for our order list, we don't have a list of Markdown elements but a list of items. So we are going to start the order list block with the OL tag and then fold the list elements using a function that takes the inner Markdown elements and the accumulator, starts a list item with the li tag, concatenates with the result of transforming the Markdown elements to HTML, closes the list item tag, and concatenates with the accumulator. And we're going to provide the empty text as the initial accumulator and apply it to the items. Once that is done, we finish our order list by using the closing OL tag. And that's it. We have the toHTML function ready to go. To use it, we just have to go back to our main module, import the toHTML function, and apply it to the elements returned by the main parser. Then we add a few more print statements for good measure and write the HTML to the output file provided by the CLI Parser using the writeFile function from the text library. And we're done! If we go back to our terminal and run the CLI again, we'll see that the HTML output appears in the console and that we have a new file called output.html. You can open this file in the browser or check its contents to verify that it was correctly generated. Congratulations, you completed the course. However, your Haskell journey is just getting started. If you don't know where to go next, I left some suggestions at the repos README. Thank you for your time and attention. I'm looking forward to see what you build.